Hey, what's up guys, this is Dr. Vivek Palipuram and I'm bringing you the next lecturette in ENGR 250, Probability and Statistics for Engineering and Computer Science. In this lecturette, I'm going to introduce you to random variables. Specifically, I'm going to introduce you to discrete random variables, and we are also going to see some properties of random variables along with its definition and how to use the probability mass function, the main probability model associated with random variables, the discrete type, to evaluate probabilities of different events. So far in our journey in ENGR 250, Probability and Statistics, we have seen different probability theorems and axioms. We have looked into the law of total probability and some techniques such as tree diagrams to solve challenging engineering problems, to solve challenging probability problems. However, those techniques were quite mathematically intensive and we had to use a fair bit of mathematical ingenuity to solve those problems. However, we are engineers and engineers are usually very good at analysis of problems and try to find out whether they are a subset of an already solved problem. If so, then we try to apply the solution of the solved problem for our current problem at hand. And random variables kind of help us in doing that because with random variables, we have something called as the probability mass functions associated, which are the generalized formula for probability for a given type of problem. And we can use this generalized probability formula to find probabilities of different events. The only challenge with random variables then boils down to finding which formula to use for a given particular problem. In addition, random variables also help us perform an important activity, and that is mathematical modeling in our computers. Now remember guys, the computers are really good at analysis of numbers, at crunching numbers, unlike humans who can not only take numbers as input, but we can also analyze non-numerical outputs like two heads or let's say it's going to rain or not, and so on and so forth. So let's talk about random variables, but before we do that, let's discuss two experiments and let's compare these two experiments. Rolling a die versus flipping two coins. As we have seen in our previous lecturettes, the sample space tells you all the possible outcomes associated with a given experiment. So if I were to roll a die, I would either roll a 1 or a 2 or a 3 or a 4 or a 5 or a 6. Whereas if I were to flip two coins, or just take a simple coin and flip it twice, I have 4 possible outcomes, and those are heads, 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 tails, tails, heads, and tails, tails. These two experiments are not only different with respect to the size of their sample space, but they're also different with respect to how their sample space actually looks like. The rolling a die experiment is a mathematical sample space, meaning that the outcomes are already assigned numbers. So such a sample space is easy to analyze using a computer. Whereas flipping two coins, we have heads, 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 tails, tails, heads, and tails, tails. Those outcomes in the sample space of flipping two coins experiments is not mathematical, or it is non-mathematical, and therefore computers will have some challenge analyzing such an experiment. So an obvious solution here, if you would like to model this experiment using a computer, then it makes sense for us to assign some meaningful numbers to the outcomes of the sample space. So far as humans, we have dealt with different probability problems and we were able to take sample space of all kinds, numerical and non-numerical. So as a human, we are able to take all the kinds of experiments and we are able to analyze sample space of both numeric kind as well as the non-numeric kind. Whereas if we want to perform our analysis on computers, which engineers and scientists usually do for large experiments, we are going to transform the outcomes or outcomes of the sample space from an experiment to numbers using a function called random numbers or random variable, and then generate numbers from these experiment which are going to be random in nature. So that's what random variables are all about. Random variables are a method of providing some numerical outcomes to the or numerical numbers to the outcomes of the sample space. And whenever we perform an experiment, instead of getting a non-numerical answer, we will usually get a numerical answer which will represent either one outcome or multiple outcomes from that experiment. This fact will get a little bit more clear as we proceed further. All right, so as I mentioned before, flipping two coins experiment gives us a non-numerical sample space, which will be inherently difficult for the computer to analyze because computers are good at analyzing numbers. So let's make it easy for our computers to analyze this experiment. And this is what we are going to do. We are going to assign some meaningful numbers to these outcomes of the sample space. There are numerous methods in which you can assign numbers to the outcomes in the sample space, but the method has to be engineering valid, or it should be valid engineering wise, and it should make sense. For example, here assigning numbers to reflect the total number of heads makes great amount of sense. So if I were to use this definition, assign numbers to reflect the total number of heads, here's how I'm going to assign these numbers. This outcome is going to get a number 2 because I have 2 heads. Here I'll get 1, here I'll get 1, and here I have 0. So when I perform this experiment, flipping a coin twice using my computer simulation, I'll get numbers either 0, 1, or 2 randomly. And these numbers represent either one outcome or multiple outcomes. For example, 2 represents one specific outcome, and that is heads, heads. Whereas 1, it represents 2 outcomes. It can represent either heads, tails, or it can represent tails, heads, and so on and so forth. Now, using these random numbers, our computers can work with probability problems. For example, after assigning numbers to the outcomes in the sample space, the number that will be generated by this experiment is going to be random. Therefore, x is a random variable where x can take on values 0, 1, and 2, and it's going to take on these values randomly depending on the experiment. In this case, flipping the coin twice. So when I say probability that x is equal to 1, or rather when your computer tries to analyze probability that x is equal to 1, it means that it is trying to calculate the probability of either heads tails or tails heads. Now this probability is equal to 1/2 because there are 2 outcomes in the sample space that have exactly 1 head. Now assuming that the coin is fair, each of these outcomes will be equally likely with probability 1/4. Using this random variable, I can answer other kinds of probability problems. For example, probability that random variable x is equal to 0 tells me the probability that I receive 2 tails, and that probability is equal to 1/4. So using this random variable value, I can calculate probabilities of different events using my computer simulation. Now from here onwards, we will not be doing explicit simulations per se, but we'll be training ourselves to eventually write some programs for our computers to perform mathematical modeling. So we will be using a lot of pencil and paper based work and work with random variables explicitly and evaluate probabilities of different events based on the values that these random variables are going to take. Now let's work on some more random variable example. Let's say that you receive a sequence of 4 data packets where each packet is either a video or a fax. What is the sample space? Devise any 2 ways of assigning meaningful numbers to the outcomes of the sample space. Now this experiment, receiving 4 packets, it's going to have a non-numerical sample space. So we need to assign some meaningful numbers to the outcomes of the sample space. Let me give you one example. The sample space comprises of 16 outcomes in this case, where I will have each packet as video or a fax, and I'm analyzing a sequence of 4 packets. So I will have 16 outcomes in the sample space, and these are just numbers, binary numbers from 0000 to 1111. So those are VV, 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 VF, if V is for video and F for fax, VV, FV, VVFF, VFVV, VFVF, VFFV, VFFF. Then I have FVVV, FVVF. Oh, this is trouble. FVFV, FVFF, FFFV, and FFFF. I hope I have all the 15 or rather 16 outcomes. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Something has gone wrong here. Okay, I see what happened. From here onwards, I should have FFVV, then FFVF, then FFFV, then FFFF. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Perfect. I have 16 outcomes in the sample space. This problem would have been much more easier for me to solve if I were to analyze a sequence of 3 data packets. But I think I shot myself in the leg here. Okay. All right, so let's assign some meaningful numbers to the outcomes of the sample space. One meaningful way is to assign numbers to reflect the number of fax packets. If I were to use X as my random variable to denote the number of fax packets, then in that case, VVVV is going to get 0, VVVF is going to get 1, this is going to get 1, 2 here, random variable will take a value 1 here, random variable will take a value 2 here, 2 here, 3 here, 1 here, 2 here, 2 here, 3 here, 2 here, 3 here, 3 here, and 4 here. Now using this value of the random variable, now the random variable in this case can take on these values 0, 1, 2, 3, 4, where 0 denotes 0 fax packets, 1 denotes 1 fax packets, and so on, and 4 denotes 4 fax packets. So if I were to ask, or if my computer were to analyze, hey, what's the probability that X is equal to 2? Then my computer is analyzing what is the probability that I have exactly 2 fax packets. Now, if each of these packets or each of these sequences are equally likely, then their probabilities is going to be 1 over 16 because I have 16 outcomes in the sample space. In this case, probability of exactly 2 fax packets will be obtained by adding the probabilities of this packet here, this 2, that's the third one, 4th, 5th, and 6th. So I have 6 packets that have exactly, or 6 sequences where I have exactly 2 fax packets. So this probability will be 6 over 16. I hope I did not make any mistake while solving this. Similarly, I can answer other questions. For example, hey, what's the probability that I receive less than 3 fax packets? So this denotes probability of receiving less than 3 fax packets. Similarly, probability that X is between 2 to 4, it denotes the probability of getting fax packets between 2 to 4. And similarly, I can have some other advanced probability setup. For example, probability that X is less than 3 given that it is less than 4. So here I'm asking, hey, what's the probability that I receive less than 3 packets given the fact that I have definitely gotten less than 4 fax packets? So in this way, we use random variables to answer different probability problems and to model different events pertaining to a given experiment. And that's all random variables are. So formally, let me introduce you to the definition of a random variable. Random variable is a function that assigns numbers to the outcomes of the sample space. Usually it's represented by simply X, but if you are more mathematical savvy, then you would use X of S, where S is an outcome of the sample space because X is a function. So when this function X takes in value, let's say VV, then value of X is equal to 0. But we'll refer to random variables simply using X. And in fact, we have seen random variables so far in our probability theory as well, whenever we performed experiments that resulted in numerical outcomes. For example, rolling a 6-sided die, the outcomes were numerical. We were observing n-bit sequences and we were interested in different things like how many number of ones we have in an n-bit sequence. The sample space is numerical in nature. I can have either 0 bits that are n, that are 1, I can have exactly 1 bit out of n bits that is equal to 1, or I have all n bits that are equal to 1. You can also have functions of random variables. For example, I can define a function which can take on a value 0 if I get less than 2 bits that are equal to 1. Otherwise, that function is equal to 1 if I get number of ones in an n-bit sequence greater than or equal to 2. So let's talk about discrete random variables, because discrete random variables are easy to analyze. Usually computer scientists are the ones that are more interested in discrete random variables, in my opinion, than any other branch. We'll start off with discrete random variables because they are quite intuitive to understand. And then we are going to turn the gear in higher mode, and we are going to look into continuous random variables, which permeates other engineering fields such as mechanical engineering, engineering management, bioengineering, and so on and so forth. So let's talk about discrete random variables. So a discrete random variable is countable in nature. A random variable x whose set is countable is a discrete random variable. For example, when I roll a die, I get 1, 2, 3, 4, 5, and 6. These are countable numbers. Additionally, a random variable x cannot take a value in between. For example, if I were to roll a die, I will get either 1, 2, 3, 4, 5, or a 6. I will never get a value that is in between. For example, I can never get a value of x is equal to 3.5. And therefore, x is discrete in nature. A discrete random variable is such that it is going to take on countable values, and between any two values in the sample space, it cannot take a value in between these two values. Discrete random variables are always countable in nature. Let's work with discrete random variables now, and let's work on this example. You're monitoring a random n-bit signal as a sequence b0, b1, b2, and so on until b of n. You count the number of ones in the n-bit sequence. Let this quantity be k. What is the probability of obtaining a 1 at any bit position is p. The probability of obtaining a 1 at any bit position is p, independent of any other bit position. Define probability of k is equal to 2 and find it, and then define probability of k is equal to small k and express it as a function of k. Please pause your video here and try to find the probability that k is equal to 2. So let me define what probability of k is equal to 2 means. Probability of k is equal to 2 means probability of getting any sequence that has exactly 2 ones, where probability of a bit being 1 is equal to k is equal to p, independent of any other bit position. As a hint, please use independent trials. You can unpause your video once you're ready. Okay, I hope you guys got the chance of solving this problem. So, as I mentioned, probability of k is equal to 2. Probability of k is equal to 2 is defined as probability of getting exactly 2 ones. Now, out of the n-bit sequence, if I were to consider one specific, out of all possible n-bit sequences, let me repeat this one more time. Out of various possible n-bit sequences, the probability of exactly one sequence that has exactly 2 ones is going to be p squared, because there are 2 bit positions that are equal to 1, each with probability p, and times 1 minus p to the n minus 2, because I have n minus 2 bit positions that turn up 0 with probability 1 minus p. That's the probability of exactly one sequence with exactly 2 ones. However, there are numerous such sequences that can have exactly 2 ones. Now, to count the number of such sequences with exactly 2 ones, I can use, or I can ask myself this question: hey, in how many ways can I fill in 2 bit positions out of n for placing my ones? Or I can ask myself, in how many ways can I choose 2 spots out of n to place my ones? And that answer is n choose 2. So there are n choose 2 such sequences that have exactly this probability, p squared times 1 minus p times to the n minus 2. So probability of k is equal to 2 will be equal to actually summation of probabilities of those n choose 2 sequences. And this probability is equal to p squared times 1 minus p to the n minus 2. So if I were to add this term, n choose 2 number of times, if I were to add this term, n choose 2 number of times, I get the probability as n choose 2 times p squared times 1 minus p to the n minus 2. So this is the probability. This is the probability of getting exactly 2 ones in this experiment, because there are n choose 2 sequences that can give me exactly 2 ones. So that solves problem number A. Now define probability of k is equal to small k and express it as a function of k. As a definition, probability of k is equal to k just tells me what's the probability that there are exactly small k number of ones in an n-bit sequence. Now I can generalize this equation right here and write probability that k is equal to small k as n choose k times p to the k times 1 minus p to the n minus k. If I were to consider one specific sequence that has exactly small k number of ones, its probability will be p to the k times 1 minus p to the n minus k. However, there are n choose k such sequences, each with this probability. So if I were to add the total probability, or if I get the total probability, I have n choose k times p to the k times 1 minus p to the n minus k. Now carefully notice this form. This form is actually a function. It's a function of k. Other parameters like n, p, they are all constant. So I can write that this is some sort of a function, probability, some probability function that depends on n and p as constants, and it gives me probability for different values of k. So because this is a function, it gives rise to a new concept called the probability mass function. Specifically, what we did here is we have derived a probability mass function, which gives us a generalized equation for the probability for a given experiment. So this is actually a generalized probability equation for this particular experiment where I am monitoring n-bit sequence. I can plug in different values of k and obtain different kinds of probability. For example, if I were to plug in the value of k as 0, if I were to place this 0 right here, that would give me the probability that I do not receive any ones in my n bits. If I were to switch k and set it to as 1, that is going to give me the probability of getting a sequence or sequences that have exactly 1 ones. If I were to plug in k is equal to 10, then I'm finding the probability of getting 10 ones out of the n-bit positions. So this is probability mass function, which is the generalized probability equation for a given problem. And we can use it to find all kinds of probabilities. So that's what we did here. We derived the probability mass function. So let's define what probability mass function is. Probability mass function of a discrete random variable is actually a generalized probability equation that gives you the probability that random variable capital X takes on a very specific value, small x. That's what probability mass functions are. They are generalized probability equations. They are generalized probability equations. And once you have them, it's a matter of just plug and chug to find probabilities. Okay, let's look into some more examples of deriving random variables and how to assign numbers to the outcomes in the sample space. For example, consider the case of flipping two fair coins. I can get either tails, 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 heads, heads, tails, or heads, heads. If I were to assign, or if I were to declare a random variable that denotes the total number of heads, then this outcome gets 0, th gets a 1, ht gets a 1, and hh gets a 2. I can write probability mass function. It is not going to be as elegant as the previous example, but it's going to be an example nonetheless. So this is another example of a probability mass function, which gives me the probability that a random variable x takes on any specific value, small x. So this is actually a probability mass function because it gives me the probability of 1/4 for x is equal to 0. It's 1/2 for x is equal to 1. It's 1/4 for x is equal to 2, and it is 0 otherwise. So this is a generalized probability equation, which gives me probabilities for different values of x. Now let's look into some properties of probability mass function. Probability mass function gives you the probability that random variable capital X takes on a specific value, small x. In the end of the day, it is a probability value. So all the axioms and theorems for probabilities are still going to be applicable for probability mass function. For example, probability that x is greater than or equal to 0 is always going to be true. If you were to add the probability mass function for all the values of x in the sample space, that should always lead to 1. It can never be greater than or equal to 0. Essentially, by adding the probability mass functions for all the values of x in the sample space, you're just adding the probabilities of all the outcomes in the sample space. That should always evaluate to 1. It should never exceed 1. Should it exceed 1, that means something has gotten wrong in our calculations. We can use probability mass functions to calculate probabilities of different events. So let's say that I have event B, which is naturally going to be a subset of the sample space. To find the probability of event B, all I need to do is add the probability mass functions for those values of X that belong to B. So I have my probability mass function. I'll plug in the values of X that belong to set B and add, I'll plug the values of X that belong to set B into this probability mass function and add them all together, and that's going to give me probability of set B. Now this will get much more clear when we actually solve a problem. So let me solve parts A, B, and C for you, and then part D is for you to submit on Thursday's class. So my probability mass function X takes this form C over X for X is equal to 2, 4, and 8. It's equal to 0 otherwise. And what I need to do here is first find C. I need to first find C, and then I need to find the probability that X is equal to 4, and then find the probability that X is less than 4. So let's work on this problem. I'll work on parts A, B, and C. Part D is for you to solve. In order to find the hidden constant C, what I can do is use the property of the PMF that if I were to add the PMF values for all the values of X in the sample space, that gives me a value equal to 1. So if I were to add the PMF value for these values of X, because this denotes the sample space, I am going to get the value equal to 1. So probability mass function is C over X. So if I were to plug in 2, then add it to C over X by plugging 4, X is equal to 4, plus C over X, X is equal to 8, that's going to give me a value equal to 1. So essentially C over 2 plus C over 4 plus C over 8 will give me a value equal to 1, which means that I get the value of C as 8 over 7. So whenever you have hidden constants in your probability mass function and you would like to find them, you should use this principle that summation of probability mass function for all the values of X in the sample space is going to be equal to 1. That's going to give you an equation, and you have just one known, your constant, hidden constant in your probability mass function, and you can find it. You will never have a probability mass function with two hidden constants. Such problems are you can never solve them. Usually hidden constant problems, you usually have just one constant that is hidden in the probability mass function. Okay, now let's solve the probability that X is equal to 4. Now the definition of probability mass function is that it gives me the probability that random variable capital X takes on a very specific value, small x. So to find this probability, all I need to do is just plug in the small x in my probability mass function. So here in this case, my small x is equal to 4. So I'm going to plug this in the probability mass function. So I'm going to plug this in the probability mass function and I get C over 4. C is a constant which I found it to be 8 over 7. So that gives me 2 over 7 as the probability that X is equal to 4. Now let's solve part C. I have an event B which is X is less than 4. So let's write down the outcomes in this event B. Let's see which values are less than 4. I have just one value in the sample space which is less than 4, and that is equal to 2. So by asking probability that X is less than 4, I'm essentially asking, hey, what's the probability that X is equal to 2? Because there's just one value, 2, in the sample space which is less than 4. So that probability will be 4 over 7. This problem would have been much more interesting if I ever had this form. What is the probability that X is less than or equal to 4? So let B be the event which denotes that X is less than or equal to 4. Then in that case, B is going to have two outcomes from the sample space, 2 and 4, because these two values satisfy this condition. X is less than or equal to 4. So to find the probability of event B, I'm going to add the PMF values for those values of X that belong to B. So 2 and 4 belong to the set B. X is less than or equal to 4. So I'm going to add the PMF value at 2 plus the PMF value at 4, giving me C over 2 plus C over 4, which is 3C over 4, which gives me, if I were to plug in 8 over 7, 6 over 7. So that's the probability of X less than or equal to 4. Using this example, what I would like for you to do is solve this problem. What is the probability that X is less than or equal to 3? My apologies. X is greater than or equal to 3, but less than or equal to 9. That's for you to solve and turn it for Thursday's class by 10 a.m. Okay. Before I let you guys go, here's what I would like for you guys to do. Carefully read this problem statement and try to use the probability theory that we have seen so far to solve this problem. So try to use all possible theorems and axioms and tree diagrams and what have you to solve this particular problem. A fair coin is tossed until you get 5 heads. What is the probability that you get 5th heads on the 9th toss? Now, when I flip the coin continuously, I can get 5 heads consecutively, in which case I will get my 5th heads on my 5th toss. I can get my 5th heads on the 6th toss. I can get 5th heads in the 7th toss, 8th toss, 9th toss. I can keep flipping this coin infinite number of times and I may never get my 5th heads. So the number of times that I have to flip here is random. So what you need to find is what is the probability that you get your 5th heads on the 9th toss. Try to use the probability theories that we have discussed so far and tell me whether you solved this problem easily or whether it was difficult to solve. I'm interested in finding out whether it was easy for you to solve or whether it was difficult for you to solve using the probability theories that we have seen so far. I think it's a good time to stop this lecture right here. I am signing off.